What's up, Coder Byte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and this week we will be continuing with part 2 of our minimizing malware question. Last week we went over some new concepts all about disjoint sets and the methods that people normally use with disjoint sets, the find method and the union method. This week, we're going to be implementing both of those methods in JavaScript, as well as actually solving the problem using what we've just learned all about disjoint sets. So if you're ready, let's get going. And in case you need it, here is a refresher of the problem. You are given a network of nodes as a graph. Some nodes are initially infected by malware. The malware will spread from the initially infected nodes to all of the nodes it's connected to, and it will continue to spread across the network accordingly. We have the opportunity to remove exactly one node from the initially infected list, which will remove it and all its connections. Return the node that, if removed, will minimize the number of nodes ultimately infected in this attack. So in case you guys forgot, this is the problem that we're dealing with right now. And we learned some new concepts all about disjoint sets. And if you haven't seen that video, part 1, I'll link it down below. Otherwise, we're going to hop right into coding all of those methods, the find method and the union method, which we will then use to solve this problem. Okay, so let's get started on this disjoint set and all of its methods that we want to code. So in my Visual Studio Code editor, I just have a very blank JavaScript file, right? And we are going to start from 0 today, everybody, no boilerplate. Okay, so the first thing I think I'm going to do is I'm going to make a class, right? I'm going to make a class called DSU, Disjoint Set Union. Now, I think this has the disjoint set part and the union in the name, because ultimately a lot of the times with disjoint sets, what you're doing is calling union on them. But I don't want you to get confused by that name. But I think this is what you'll see online and in different textbooks and whatever, a DSU, a disjoint set union. So I'm going to start with my class, and I'm going to call it DSU, right? That just stands for disjoint set union. And with any class, we want to talk about its constructor, right? So what are we initializing this disjoint set with? Now, in this case, what we're going to want to do is we want to have an array, right? We want to have that array of initially at least -1s, right? So we want to somehow know how big is this array going to be, right? Otherwise known as how many nodes are in this graph, or how many individual nodes are going to be the building blocks for our various components, right? Because each one needs to have an index in this array. So the first thing we want to do is pass in a size, right? And the size, I think, is going to be just how big do we want this disjoint set to be. And that just is going to determine how large this array is going to be, how many individual nodes are going to be grouped in different ways. So right away, we have this size, right? And we can do something like this, right? We want to have that array. So that's going to be the thing that's tracking the components, right? So we can call that this.components. Pretty straightforward. And we are going to make this array have a size of the size that we passed in, right? So we can make a new array with that size passed in, and we can fill it with -1s, right? We want to initialize it with all -1s, always with our disjoint sets. We're going to have all of our components be separated. Not always, of course, right? Sometimes we might already have some components that we know of, but we'll get to that in a little bit. So for now, we have our DSU. When we initialize it, we're going to give it a size, and what we get back is an instance of this class, and it's going to have a components property, and it's going to be that array with all -1s. Okay, so that should be simple enough, right? Now, in terms of our methods, right, what do we want to make? We want to make find, right? And we want to make union. Those are our two methods that we are interested in making right now. So let's do find first. Find, what do we want find? Find is, of course, now I think I want to stress this because it confused me at first. Find does not find the node. Find is actually find the parent of the node. So it's commonly referred to as find, but in my humble opinion, I think a more accurate name here would be find parent. But whatever, we're going to leave it as find, but I'm going to make a comment here so you can remember this is actually find the parent of the node, right? So of course, probably we're going to get a node, right? Because we're going to be finding the parent of that node. Now, if you remember from our last video, this is going to be recursive, right? We're not only going to be checking this array at the index of the node, we need to continue to follow the trail, right? Just like a linked list, because each one might point to another parent until you get to a negative, right? So I just said two different things that should have, ding, ding, ding. So I said that we're going to recurse, right? And then I said that until we get to a negative, right? What does a negative mean? A negative means that in that node is its own parent and we've reached the end. That is the parent, right? So we're always going to be recursing until we reach a negative because that's the definition of a parent in how we've defined this. So that's our base case, right? If this is going to be a recursive function, that's going to be our base case, that we've come across a negative number, right? So we can fill that in right away. This is just going to say if, right, this dot components, because that's the array that we're searching through, at that node, right? So remember, each index of the array is going to signify that node, right? So if at that node, we've finally reached something that is less than 0, right? And that's going to cover whether or not it's a -1 or a -2 or a -10, whatever. If it's less than 0, it's a parent, right? So we can just return that node at that point, right? And that is our base case. We want to continue to search through this array until we eventually reach that, right? Okay, so I hope that makes sense. And what do we do if we haven't found a negative? We call this dot find, right, on whatever is at that index at that point in the array. So that if one node has a parent of another node, which then it has a parent that has a negative, we continue on until we get to that parent, right? The negative parent. So we can just return here this dot find, and what we want to do is we want to pass in the next one in the chain, right? So that's going to be whatever is at this dot components at that node that we've passed in, right? And that will be the next node in that linked list, so to speak, of nodes. And that's it. That's find. So find is super simple. So let's just, show some examples here of what we're going to have at the end. So I'm going to say const testing equals new DSU, and I'm going to give it a 10. Why not, right? So again, that's going to make a DSU with an array of length 10 with -1s all filled in. So let's just see what that is, right? Testing.components. Let's see what that looks like here. And here we have our array of -1s, right? And obviously we can't affect any of them until we fill in union, but I do just want to point out that if we console log now, testing.find, and we pass in 5, let's say we're going to get -1, or we're going to get 5, right? Because we're going to hit this negative. This is a negative at that index, and then we're just going to return the node, right? Okay, so again, can't test much more until we make this union function. So union, let's hope it's as simple as that find, right? So we have a union, and remember, we're always calling union between two nodes, right? So let's say we're going to pass it node 1 and node 2. Now, what are the rules of union? Union, the rules are, right, we use find, right? We call find for each of the nodes, and we say, what are each of these nodes' parents? If it's the same parent, do nothing, right? Or depending on the algorithm, right, like that could be where you return, hey, there's a cycle here, or whatever. It depends. But for us, we're just going to do nothing if it's the same. If it's not the same, the first thing we're going to do, right, is we are going to take the value, the size of the second node's component, and we are going to add it to the first node's component, so that before we call union on them, we can accurately increment the size of the first one by the size of the second one, right? Before we make it part of the same component. So that's the first thing we're going to do. And the second thing we're going to do is we're going to set the parent of the second node to be the parent of the first node, right? That's all there is to union. We're making these two different nodes part of the same exact component, aka they're going to have the same parent, right? So I said this in the first video, I want to say it again here. That's arbitrary, that we're making the parent the first node, right? We're making the parent of the second node the same as the parent of the first node. We are kind of slurping that second component into the first component. You could do it the opposite. The parent of the second node becomes the parent of the first node. You can do it based on size. Whichever is the bigger component can become the new parent. It depends on the problem. But for us, for right now, we're making the parent of the second node is now going to be the same as the parent of the first node. Okay, so let's see if this is as easy as I promised. So the first thing we are going to do here, right, is we are going to call find on each of these, right? So we're going to say const parent node 1 equal this dot find node 1, right? And then we're going to do the same. Const parent node 2 this dot find node 2. Okay, so that's simple enough. We'll get the parents of each of those nodes, right? Now, we only want to actually do the union if they're not already in the same set, right? So we can do a simple if here, that if the parent of the first node is not equal to the parent of the second node, right? And only really do anything if that's the case, right? Now, what do we want to do? We want to get the size of the component of this of the second node, and we want to add it to the size of the parent of the component that the first node belongs to, right? So here we have an opportunity to do that, right? So we can say that the size of node 2 component, I hate when there's a number in the letters in a variable name. Comment below if you agree, but oh well, too bad here. So here we can just get that, right? We have access to that. So we can get that from the this.components array, wherever that parent node 2 is, right? Because that's what's being tracked in this array. We're tracking who's your parent, and if you're your own parent, what size is your component, right? How many children do you have? Those are just the rules of the array, right? So we can grab that here, right? That size of that second component, and we can add it to that first component, right? So we can say this dot components at the parent of node 1 plus equals that size of that second component, right? So that's the first thing we're doing. We're keeping track of that size, and we're not losing that in the union. Before we union, remember what that size was of that second component, and let's add it to the first component. Okay. And the second thing is, again, pretty simple here, is we are going to set the parent of that second component to be the parent of the first component. That's the definition, right? That's what makes it be in the same component. So we can say this dot components at the parent of node 2. We can just set it equal to the parent of node 1, right? And that's it, we're done. So just with those two simple steps, we are able to call union between two disjoint components and still maintain the size, and also continue to have this pointer of now I'm attached to the first component. I was attached to myself, but now I'm attached to the first component. And remember, even if at some point we are dealing with a node that is in the middle of its linked list of, who do I belong to, find will take care of that with our recursion, right? Find will eventually get to the actual parent, the one node that has that negative, because there's only ever going to be one node with a negative, that's the parent, and all the other nodes are going to point to it or point to each other that point to it. So I hope that makes sense for everybody. And again, I think that if you really understand the concepts behind these algorithms, the functions are actually very simple. So if you're having trouble with the concepts, go back to our first video and come back here and see that the actual mechanics of this are fairly straightforward. So let's walk through an example of using our brand new union method. Okay, so we have our DSU with a size of 10, right? And that's going to have an array of 10 negative ones, right? And we find 5, we get 5. That's exactly what we expect. Okay, so let's try testing this out a little bit. So let's say testing.union, and let's make a union between, let's say, 2 and 3. And let's see what happens there. So let's clear this and let's do node malware.js. Oh, and of course, after we call union, we want to console.log testing.components, right? Okay, so this is what we initially have, right? This array of 10 negative ones, right? And here's our log from just when we did, console.log find 5, right? And then here is after we called union between 2 and 3. So let's go to the 2 index and the 3 index. So 0, 1, 2, and then 0, 1, 2, 3, right? So that's these numbers right here. Okay, so the first thing you'll see is that at the second index, we have a negative. That's good because we still maintain that 2 is the parent. But it, instead of having just one child, now has 2 children because 3 is now in this component, right? And that is signified by there being a 2 in the 3 spot. And then we can go a step further and say console.log testing.find3, and we should get back 2, right? And we do. We get back 2 because 3's parent is 2, and that's what we expect. And I want to clarify, before when I said that there's only ever one negative, of course that's not true. There can be as many negatives as there are, every one of them can be negative, and then we just have a bunch of nodes that are not part of a component. What I meant to say is that there's only ever one negative per component. So in this component, there may be many things that point to 2. There might be some things that point to 3, right? Actually, why don't we just look at that? Let's do that right now. Let's do testing.union. Let's do 8 and 9. And let's console log that out. Okay, cool. That's obviously not what I meant to log out, but thank you, Visual Studio Code. Okay, let's try one more time. And okay, so we have a bunch of components that only have 1. We have the original component we made, right? And now we have this new component, right? So now 9's parent is 8, as we would expect, and then 8 is a parent and has 2 nodes in its component, right? So now what do we want to see? We want to see that, that linked list, right, of the components pointing to it, the different nodes pointing to each other. So to do that, let's test out, let's call a union between, let's say, 8 and 3. Let's try. And then let's log that out. Okay, so what happened is now 3 has a parent of whatever 8 had a parent to, right? So what we've done is we've said 0, 1, 2, 3 now has a parent of 2, which has a parent of 8, right? So that does test out it does show what I wanted to show, even though I was going to do it the opposite. I was going to make 3 a parent of 8. But what I wanted to show was this kind of pointing to each other, and that in this component that all of these nodes are in, there is only one negative, right? And that's that this -4 is ultimately the parent, and they all point back to it, even this one, which first points to 2 and then points to 8, right? So let's just also show what find would give us. So let's say testing.find, and let's say 3, and we should get 8, right? Even though it's at its index, it points to 2, and we get 8. So I hope you all think this is as cool as I do. We're about to use all of these new methods in our minimize malware function. Get ready. It's finally time. Let's hear, how does this relate to our malware problem? Okay, so on your screen, you should see a graph. This is the same graph I used as the example when I walked through exactly what the problem was asking in our previous video, right? We have a graph, we have 0, 1, 2, 3, 4, 5 nodes, and we get an array of initially infected nodes, right? So that's going to be 1, and 2. So let's see that in red here, right? Okay, so now that we know everything that we know all about disjoint sets, maybe you might say that some of us here at CoderByte are experts, right? If you've been watching our videos, just kidding, always keep learning. You might see right away, hey, wait a minute, there are components here, right? I see 0 as a component kind of all on its own. I see 1 and 2 as a component, and I see 3, 4, and 5 as a component, right? And you can remember that the question is asking, which node should we remove so that the overall health of the network is maintained, right? Like, we're trying to minimize the spread of this malware. What that's actually asking with this new lens that we now have, now that we know all about disjoint sets, is when we add in each of these nodes, which one of them becomes part of a bigger component, right? Because that's the one we want to remove. Because if it's going to affect a lot of other nodes, aka share the same parent, be part of the same component, then that's the one that's going to have the most devastating effect on the network, right? Because it's connected ultimately to the most nodes. So let's see that in action, and then we'll talk through exactly the algorithm we're going to use here. So the first part of this algorithm is to get rid of the initially infected nodes altogether, right? Let's just think about our graphs in terms of the clean nodes, right? So here we have 0 and we have 3, 4, and 5, right? And you can imagine that we can remove those initially infected nodes from the graph, right? And then we can create disjoint sets out of these remaining clean nodes, right? So that we know what we're dealing with. So in this case, we would probably add 0 as its own, right? And then we might add 3, 4, and 5, and we would call union between 3 and 4 and 3 and 5, right? Okay, so let's see. Add our clean nodes and their edges to a disjoint set array. So I hope that makes sense to everybody. At this stage, we have this array here, right? And I'll explain why in a second. We actually have an array of the size of the entire network with the other nodes included, the infected nodes included in it, but we'll get there, 1 second. So we go to our 0th node, right? And it is its own parent. Remember, ignore 1 and 2 because they are the initially infected nodes, right? But they're here as well, know that. And then we have our other remaining component, which is of size 3, right? And 3 is the parent of that, and 4 and 5 both point to it as their parent. Okay, so those are our first 2 steps that I hope people are understanding. With those other initially infected nodes gone, what groups are at play here? What are the different pieces of our graph and our network? Okay. Our next step. For each initially infected node, add it back to the clean graph, aka call a union between it and the nodes it's connected to. So we have our nodes, right, our clean nodes, and we have our disjoint set array that we're tracking these nodes in and the different components, right? And now for our algorithm, we want to see what do each of these infected nodes what effect would they have on this network, right? And I think that's very important here. And there are different ways to solve this problem, but I chose to go with a solution that I thought was it was the easiest to understand. And for that, I decided that I am going to have each infected node, I'm going to add it to this array right here. I'm going to add it one by one, right? And each time I'm going to see what does that do to the disjoint set that I have. So in that way, I'm duplicating this clean disjoint set for each infected node that I'm adding. Again, because I want to see what happens to the nodes with the addition of an infected node in isolation. So if you didn't understand anything I just said, it will become clear in a second. So let's see what happens if we add node 1. So here we add node 1, right? So what does that mean? What did I say? We're going to call union between it and the nodes it's connected to. So that would mean that we're going to call union between 0 and 1, right? And that's the new disjoint set array that we're going to have that's tracking that. Because this whole thing, right, we only want to know what happens if we add one at a time. Because we want to know which one to remove. So we want to keep track of the effect each infected node will have on the network individually. So we add it, right? And we can see here that 0, right? 0 now has a parent of 1, and 1 has one child, right? It and 0. So, okay, that's great. The rest of the graph stays the exact same, right? Okay, so what happens if we add node 2? And remember, this is duplicative. I think that's how you say that word. We're gonna, see this happen twice, because now we're gonna add 2 to this, not this. This is also going to happen, right? Because we're gonna compare them in just a second. But okay, so we add 2 to the, we add 2 in all of its connections, right? So let's call union between it and the parent of 3, right? Because it has a connection to 3. So that means that 3 is now going to have a parent of 2, and 2 is now going to have 4 children, right? So let's see if that's right, and that is right. So now 3 points to 2, and then this has 4 children, right? Okay, so now we have both of these two options, right? These are our 2 different ways that the 2 different nodes affect this same clean disjoint set, right? So there I'm putting 1 back just so you can remember what that looks like, what the visualization is. And what's our last step? Our last step is to check the sizes of the components at each of the infected nodes. The ones with the largest size will be the one with the most impact on the overall network. This is the node we want to remove, right? So because of disjoint sets, we are tracking the sizes of these components as we call union, right? When we added 1, we were able to track that the size was 2. When we added 2, we were able to track that the size was 4, right? And at this point, it's very simple. We can just check which node became the parent of the biggest component, right? And that's the one we don't want to add. That's the one that the malware is going to spread to the most. So let's see that, right? So if we add node 1, we'd get the size of 2. And if we add node 2, we get the size of 4. Definitely remove the second one, right? So we're about to do this in code. If you didn't follow from a conceptual standpoint exactly what I just did, I invite you to rewatch this portion of the video, because the code, again, hopefully like the find and union methods, once you understand the concept, I think the code becomes significantly cleaner and easier to follow, and actually relatively straightforward once you really kind of get what's happening here. And if you're ready, let's go code this out. Okay, I hope everybody is ready to code this problem. Okay, so the first thing we're going to do, right, is right now we are in this DSU class, right? This is still from before, from when we implemented that find and union method. So we're going to use this in our function, but we're not going to make this a method of the DSU. So here I just have added some test cases and we will talk about the function parameters in a second. But let's go ahead and define this function right here. So we can just say function minimize malware spread and call it a day. We're done. Just kidding. Okay, so let's talk about this minimize malware spread. So we are going to take two parameters, right? The problem says that we are going to get the entire graph, right? All of the nodes and all of their connections. And then we're going to get a list of initial nodes that are infected with malware, right? So what we're seeing here as this first argument is the entire graph. This is modeled as an adjacency matrix. Again, if you need review on how an adjacency matrix works, please definitely check back to one of our earlier graph videos where I go into this in depth. But essentially, every single subarray represents a node in the graph, and then every single index of each subarray represents whether or not there is a connection to that node, whatever index we're at in the subarray. A 1 denotes that there is one, a connection that is, and a 0 denotes that there is no connection. Okay, so that's what that is, number one. And number two, we have this list of initially infected nodes. Now here, I don't want you to get confused and say, oh, more zeros and ones. What is that? This is a list of the nodes that are initially infected. So when we get an array with a 0 and a 1 in it, that's just coincidental. We could get an array with a 2 and a 3 in it or whatever, but in my examples here, I have the 0th node and the first node being infected actually each time in every test case. So what that means is this 0 is referring to this node, right, in the graph. And this 1 is referring to this one in the graph. Okay, so those are the two things I wanted to kind of go over straight from the start. So let's go ahead and define these parameters, right? So we're going to call that first thing the network, right? That is the network of nodes. And the second thing we get is that initially infected list, right? So we can call it initially infected. I think I like that variable name for that. And what we want to do, right, if we, rewind a little bit to the slides, is we want to use this DSU. We want to initialize a DSU for our graph for all of the clean nodes, right? All of the nodes that have not been initially infected, so that we can start to see where are the components here, where can we separate pieces of the different graph, the different network, right? And then we can start to, play around with adding in these infected nodes. So that's what we're going to do from the start. We're just going to initialize a DSU, and that it's going to be the size of the entire network. Okay, so right away, right, what does our DSU take, if we remember? It takes this size, right? Because that's how it knows how to initialize its array of components, right? So we want this to be the size of our entire network. So we can say, const network size is the network.length, right? That's super nice about this way of representing a graph, is that we can just take that off just as its length, right? Because it's just an array. And then we want to initialize a new DSU, right? So that's as easy as saying that the, const network DSU, we can call it, is going to be a new DSU, right? Nope. There we go. A new DSU with that network size, right? That's what we want to initialize it to be. Okay, so easy, right? We have all of these components, and right now they're all modeled as disjoint sets. They are all their own parents, and they're just the size of one, right? So what do we want to do here? We want to start to, add those connections in, right? Add those edges in, and that's how we're going to start to see the various components of our network here in this problem. So that's pretty easy, right? All we have to do is loop through, right? Loop through each of these arrays, and then call union whenever we get to a 1, right? Call union between the node that we're, at in the original array, and then call union with it and whatever index we're at in the subarray, right? So in this case, this would be this one, right? So you'll see that in a second, but just so you can kind of, start to think ahead a little bit, this is going to be a nested for loop, right? Because we're going to loop through each of the nodes, and then for each of its connections, we're going to call union with a few different caveats, which we'll talk about. Okay, so let's do that for loop, right? For let I equal 0, I is less than, let's say, that network size, right? Because we're going to loop through that whole thing. I plus plus. Okay, so we have our for loop, right? Now, here's our first caveat. What did I say? We're going to be adding all of these components, these connections between the nodes, but we don't want to add the initially infected nodes, right? We only want to add those at a later step when we're ready to track how big each component is when we add the initially infected node as its parent. But we need to make our components first, otherwise it's meaningless. So before we even continue, right, at this stage, even at the outer for loop stage, if this whole thing is the initially infected is in the initially infected list, right, which in this case it is, skip it, right? Don't continue. Go to the next iteration, right? We want to add all of these connections. So the way I'm going to do that is I'm just going to check if in that initially infected list, the index of, right, I, right? And what that does is, because I, again, is keeping track of where we are in this array, that if, let's say, take an example, right, we're at the 0th here, it's in our initially infected, right? 0 will be our I, and that's how we can tell whether or not it's an infected node from the get-go. So we can check whether or not that is in this list, right? So if it's greater than -1, it's in this list. I'm going to say continue. And I don't know if you have heard of the keyword continue, but continue is something that that you can use to basically not break out of the for loop entirely. That's another keyword that people use, but just skip to the next iteration. So if we're at 0, it will skip to 1, right? So that's really useful. I personally have just started using, break and continue a bit in Python at my day job. And so, cool stuff. Okay, so if we have an initially infected node, skip it, right? Forget it. But if not, what do we want to do? We want to loop through its connections, right? So let's say const connections are the network at I, right? So that is grabbing hold of that subarray, right? So now I'm saying, okay, we're at here, right? This is all of 0's connections at this point, right? Okay, so that's when we want to start our second for loop, right? Because we're going to want to now loop through these connections. So we can say for let j equals 0, j is less than connections.length, right? That's how long we want this for loop to go for, and j plus plus. Now, what do we have to do here? We want to call union, right, between essentially I and j. But we only want to do that if both I and j are both not in the initially infected list, right? Because even though we might have skipped the entire, initially infected node, we don't really want to add any connections to the initially infected nodes yet, right? That's again something we are going to save for a later step. Right now, we are entering in our clean nodes, our totally not infected nodes, and anything that has to do with the initially infected nodes, we're saving. So here, we also want to do a little continue step here, that if the initially infected list, right, if the index of j is greater than -1, right, if it's initially infected, the connection between I and j, we also want to continue here, right? We don't want to, whatever we're about to do, skip to the next iteration. Now this continue will skip to the next iteration of this for loop, right? Because we still want to continue down all of I's connections at this point. This continue will skip to the next iteration of this for loop. So we can totally bypass looping through all of the connections if it's an initially infected node from the start from I. So I just want to point that out. Okay, now the next thing is, right, very easy. If there's a connection, right, if there's a 1 there, so because it's ones and zeros, we can just do a pretty easy, if connections at J, right? Because if that's truthy, that means it's a 1, and if it's falsy, that means it's a 0. So if it's truthy at that point, what do we want to do? We want to call, right, network DSU dot union I and J. So what that will do is it will actually make the connections in our disjoint set, our instance of our disjoint set that we've initialized up here, right? And so in this way, we will have our various components, and it will just be our clean nodes, right? Our uninfected nodes. And so if we want to see what we have so far, I'm going to comment these out and we can just focus on this first one for now. But we can see at this point, console.log, what does our network DSU look like? Okay, so let's keep that there. Let's do this. And let's see, node malware. Okay, so we have all -1s. What does that mean? So that is because I think we have, right, because our initially infected nodes are 1 and 2, and then excuse me, 0 and 1, right? 0 and 1. And then this second node right here, 2, has its only connection is to one of the already infected nodes, right? So it's -1. So I wanted to include that as an easier example, but let's look at a different example to show you kind of what this disjoint set is going to look like at this point. So this is a little bit of a longer example here, right? So let's see what it looks like if we call it. Okay, so essentially, right, so for this one, our initially infected nodes are 0 and 1, right? So 0 and 1, those are out. They have -1s. That's great. And then for the second and third node, the second node is connected to the first node, right? That's denoted here. So we don't have any reference to that because we skipped it because we're not including infected node connections right now. But what we do have is we have a connection to, oops, I don't want to move that. What we do have is a connection to our third node, right? And that is denoted here and here, right? They're connected to each other. And so this node points to 2, right? And then this node has a size of 2, which is exactly what we would expect. Okay, great. So we have our, initially our clean state, right, so to speak. This is the state of the network when there are no malware nodes added into it. So the next part of this algorithm is to now add in those nodes that were infected, and we're going to add them in one by one, right? So again, this is going to be an expensive operation in terms of space because I'm going to make a separate DSU for each infected node. And we are going to look at what does that look like compared to what are the other DSUs look like when we add in the other nodes. So I just want to say that right off the bat. I think this is the most clear solution. It's a very clear way of visualizing things, and I think it's useful for teaching. But if you can come up with a solution that takes less space, please be my guest. Definitely try and solve it different ways. There are a million ways to solve this problem, and I would love to see what everybody comes up with. But I just want to say that off the bat. So let's get rid of this console log, right? So this part, I think what we want to do is we want to provide a way of creating a DSU with a already pre-initialized state, right? Because we kind of want to copy each of these DSUs and then add in the node one by one for each copy of the DSU. So right away, I know that we didn't add this functionality in our DSU, right? We always start our DSUs with just arrays of -1s. So I think of instead of doing that, we can take like an initial first state, right? So we can take in an optional components, right? And we can set it to -1, or we could set it to whatever the components we passed in are, right? So that's pretty easy in JavaScript. You can actually just do this. And what that will do is if we pass in a components array, use that as the components. Otherwise, fill in an array of -1s. So that allows us to initialize a DSU with a pre-existing state. So, easy addition and something that's going to be useful to us right now. So let's go back to our function minimize malware spread, and we are going to go right where we're ready to kind of add in those infected nodes. So we want to maintain that, what is that clean state, right? What is the state of the network with none of the initially infected nodes in it? So that's going to look like this, right? Const clean state. And that's going to be what? That's going to be the network DSU that we have right now, its components, right? That's going to be the array of components that we've just constructed here, right? And I think I'm going to add some comments just to make this a little bit clearer, that here we are adding in our clean nodes, right, to a DSU. So this is tracking our components, our clean components, without any of the initially infected malware components. Okay, so we have our clean state, right? And now what we're going to want to do is we're going to want to add in one by one each of those initially infected nodes. So that's going to actually look very similar to what we did up here, right? Because it's the same logic of go to the initially infected node, and then for each of its connections, call union. It's the same with a few small differences. So bear with me here. So we're going to say for let I equals 0, I is less than initial dot length, right? Initially infected nodes dot length, because we're looping through the initially infected nodes at this point, I plus plus. Okay, so we have our outer loop, right? So the first thing we want to do is for each of these initially infected nodes, we want to initialize a fresh, disjoint set union, right? And that's because for each of them, we want to see what does this do to the network, just this one node, because the question asked us which one node do we want to remove. So we really want to see them in isolation here. So the first thing I am going to do is I'm going to make a new DSU, and I'm going to call it fresh DSU because this is like a new one. I don't know. We're going to say we want a new DSU. We want to pass it the network size, which we have from above, and then we want to pass it that clean state, right? So that is just taking what we saved from above and passing it in here, which will, like we just set it up to do, we will set that to be the this.components if it exists, if we pass it. Okay, so we have our fresh DSU. Excellent. Okay. And similar to above, right, we want to say that our const infected node that we're dealing with here is going to be whatever the initially infected list is at I, right? So we're looping through this array now. So we want, right, we want 0 or 1. Now in this case, I would be 0 and initially infected at I is also 0, same with 1. But we might have gotten something that had a 2 there or whatever. So we want to take the initially infected node in the list, which is 2, which may or may not be the same as our I. So we'll just look at whatever's there. Okay. And then we want to say what const connections, right? This is the same as above. This is going to be whatever the network is at that infected node, right? Nope, infected node. So now we have a, a pointer to connections, right? So if we got the 0th infected node is 0, we're looking at these connections, right? Okay, so this is all the same as above, right? So again, similar to above, we're going to start another loop, right? So let j equal 0, j is less than connections.length, j++, right? And now we are going to loop through the connections. Now, we did not check to see whether or not the node was initially infected and then to continue like we did above in this outer loop, right? Because we know that it is initially infected. That's why we're looking at it. So we don't have to check for that. But here, we only really want to call union between the infected node and the clean components, right? We don't care if it's connected to another infected node, right? So here we can check again for, and this is going to be similar to what we did above. If initially infected dot index of j, right? So that's going to be the subarray, right? So if the index of j is greater than -1, we want to continue because we don't want to add anything we don't want to add any connections between an infected node and another infected node because we're going to add that other infected node in a fresh, right? We're going to make a fresh DSU for that node, and that's going to be a different iteration of the I loop. So between infected nodes, don't add those connections. Okay, so we've taken care of that, right? Now, if there's a connection at j, this is the same as above, right? If there's a 1 or a 0, so if there's a 1, we want to call, right, fresh DSU.union between the infected node and j. So this is where the magic happens, right? This is where we are saying all of the infected nodes connect it. Make the infected node the parent with any of its edges. And now we're going to check what's the size, right? That's our last step here. This is just adding in each infected node and creating unions between them, right? And the thing we really want to look at here is which one caused the biggest component to form, right? Okay, so what do we want to do? We kind of want to know two things, right? We want to know the worst possible, we want to know which infected node created the largest component, right? And we want to know what was the largest component because we have to compare them somehow, right? So up here, I think what we're going to want to do is we are probably going to need some variables, right? Because we're going to want to track a biggest so far, right? A worst case so far, so that we can compare them so that at the end we can return that. So I think we want two different things, right? We want our worst case, right? And that's going to be 0. And then we want our worst node, right? And I'm going to set that to null at first. So in this case, this is our worst case, our worst possible component size, right? So we can even say this is the worst size. Or maybe even like smallest size, right? That's confusing. Because remember, this is going to be negative numbers because that's how we denote size in these arrays, right? So when I say largest, it's really going to actually be the smallest number at that index, but you'll see that in a second. So let's say worst size, because I think largest and smallest here is confusing for the concept behind this algorithm. So we have our worst size and our worst node, right? So after this loop, we have right here, we have an opportunity, right, to check that size of the component created from adding in the infected node, right? So we're still in the iteration of I, right? So this is the opportunity to check the size that when we added this node and all of its connections and made it the parent of anything that it was connected to, this is when we have our DSU, we have our components that we can check, hey, what was the size after we did all of that, right? What kind of group did that create? So at this point, we can check something like this, right? So we want to say that the worst case, right, the worst size is going to be, again, now this is going to be a minimum. Don't let that confuse you, because the minimum really means the largest size, because these are negative numbers, right? So the worst size is going to be the minimum, min, of the worst size that we have, right? And what do we want to compare it against? We want to say that fresh DSU, its components, right? What is the size of the component for the infected node, right? That's what we just added. So at this stage, and we can do some console logging in a second, at this stage, we have our DSU, and we've made our infected node the parent of everything it's connected to. So it's going to have a size, right? It's either going to be alone, it didn't have any connections, and then it's a -1, or it's going to have some number, right? -2, -4, and that's going to signify that when we added it, it became the parent of a lot of other nodes. So at this point, we want to take the minimum between the worst size that we've gotten so far, right? And whatever this current infected node, whatever its size is. Okay, now the other thing we want to do is we want to keep track of the worst node, right? Because we don't only want to know the size, we want to know the worst node, right? So we can do that as well. We can say if the fresh DSU dot components at infected node, right? If it is less than the worst case, the worst size, excuse me, right? So that's, again, checking that size comparison. If that's the case, then this current infected node is the worst one, right? So now the worst node is now the infected node, right? So the worst node equals that infected node. And in this way, we will also be able to maintain that based on the worst size, which is the worst node to add, right? So I hope that's clear. We can console log out some of what's happening here. But after we do this for each of the initially infected nodes, we can actually just return the worst node, right? And that's our answer. So let's see what happens here. What do we want to log out? So I think we should log out here. We want to log out, right? We want to see the fresh DSU dot components. And so we can see kind of what happens after we add in one of the initially infected nodes. And I think that's really mostly what we'll want to see here. So let's see, and why don't we also just log out here the clean state, right? So that will be the network DSU dot components. So this is going to be, let's label some of these. This is going to be the clean state. And then this console log this is going to be after infecting the network with, and I think here we want to call, and let's change these. So this is going to be our initially infected. That's not true. This is going to be our infected node. There we go. So after infecting the network with this infected node, right, we're going to get what it looks like. Okay, so let's see this first one here. Now remember, we're also expecting this to return 1, right? Because if we have 0 and 1 have been infected, and 1 is connected to 2, and 2 is connected to 3, right? we want to definitely remove 1 because 1 is going to infect 2 and 3, and 0 is only going to infect 0. So let's see that in action here. Let's give us some room. Okay, so we have our clean state, right? And let's look at our input again. So we have those connections, right? After we remove those first 2, the only connections we really care about is that there's a connection between 2 and 3, right? Which is signified here. When we infect the network with 0, we have the same exact thing because we don't add any of its connections because none of them are to any of the other nodes, right? So that makes sense. And then when we add in the second one, right, when we add in the first node, right, number 1, what happens is we set that it is now connected, right, to 2 and 3, right? And now 2 has a parent of 1, and 3 still has a parent of 2. But the important thing to note here is that when we add this component, we have -3, right? Now, -3 is the size of the component that's created when we add in that infected node, and that's definitely our answer, which is why we're getting null. Let's see, why are we getting null? Okay, so we have our worst size, right? So we take the min of the worst size and the fresh dsu.components at infected node. So let's console.log out. What does that worst size look like? Okay, so it's -1 and then it's -3. That's great. And now if the fresh dsu.components at the infected node is less than the worst size, then the worst node should be the infected node. So why is that not working? Okay, so it's never getting in there. So I wonder why that is. Okay, so we have our fresh DSU, right? And we have our components. And we have our infected node, right? Aha, because at that point, it is not less than the worst size, right? So at this point, the worst size, we've already set it to be the same, right? So we need to move this up a little bit. That's my bad. And now let's see what we get. And then we get a 1. Okay, perfect. So I hope that made sense to everybody. I'm going to get rid of some of these logs. And we can just make sure, run our test cases that they all work. Okay, so for our first one, we want to remove 1. That sounds right. For our second one, we want to remove 0. That also sounds right. And then this last one we just talked through together. So I hope this made sense. I think that, again, this is a kind of more complex topic, but if you really understand the concepts here, the code actually becomes it's easy. It's loops and other loops, right? Like we all know how to do for loops. This is not recursive. This is not no combinations. So I think that where this algorithm shines is that you're using that DSU, which is another very simple structure, to track this complex topic, right? This idea of grouping the network in different ways and playing with the edges so that you can figure out, how the whole entire network changes based on the removal or addition of a node at a time. And of course, I can't let you go without talking a little bit about the big O of this algorithm. So what is the time complexity and space complexity of this algorithm? So our time complexity here is a big O of n squared, right? Because where n is the amount of nodes in the network. Because for every single node, we also need to loop for every single connection, right? And it could potentially be connected to every other node. And so the way this algorithm grows is exponential. Now, in terms of our space complexity, I think our space complexity here is a big O of n times n, right? So how did I get to that? N is the length of the initially infected nodes list. So this is going to be we are going to have to create a disjoint set, right? An instance of our disjoint set union class for every single initially infected node. And with every single initially infected node, we are also going to have to track how many that disjoint set is going to grow by the number of nodes in the graph, right? That array that disjoint set has inside of it is going to grow with M, which is the size of the network. So important to keep in mind, this is an expensive algorithm. Again, I think that it is a very cool application of some various topics. But please definitely leave your solutions in the comments below if you come up with anything with a little bit better stats. If you've made it to the end of this video, congratulations. This was a long, very dense 2 videos, and I really commend you for joining me and trying to learn something new and practicing all of your skills coding. I think what the lesson I want to leave you with is that it is really important to take breaks. I think that there are some topics that it doesn't take just one YouTube video, just 2 YouTube videos. It might take 20 YouTube videos. You might be practicing something for a really long time before you really understand it. I know there are so many things in coding and in life that I've had to come back to over and over and over again to really actually learn what the, underlying pieces of the puzzle were. So I'm leaving you with this message. Make sure you walk away from this computer, even if you don't understand this yet, come back to it. Some things that are really worth knowing, you have to come back to a few times. And then once you get it, it's really, really satisfying. So please continue to come back to our channel, keep doing all of this hard work. It really does pay off. And I will see you in next week's video. Have a good week, everybody.